All right.
Thank you for the help for that.
Yeah, of course. All right. So everybody, this is the recording of our accuracy checks, which usually is, I won't lie to you, it's much better in person as a lab, so that you all can sit and demonstrate to me that you understand what I'm talking about. But here, at least in this format, we get to record, so you can watch it however many times you need. I've actually created a new accuracy check, updated one for this semester. So let me just pull that up. I cleared up some weird issues with the slides, so stand by real quick. And project, great edits. Okay. So while that's opening up, after class is over, I'm gonna do accuracy checks. We're gonna talk about the concept of the accuracy check. I'm gonna stop the recording after I get all your questions recorded here. And please feel free to stop me and ask questions while we're going through this, because your classmates that aren't able to make the live classes probably have the same exact questions as you. So do not hesitate to ask me. Hey, that doesn't make sense. Stop and explain that again. We have all the time in the world, right? In theory. And then after I'm done and gone through all the accuracy check slides, I'm gonna stop the recording, restart the recording, and do ETOPS. Like you guys saw, I just sent an announcement out with my YouTube channel for AS350. Some of you said you weren't getting or didn't realize that I had attached the videos to each announcement. So you can just go on YouTube and go to my name, Michelle Height, and you'll see my channels. So in case you really want, you're in both classes. I have a 411 channel and I have a 350 channel. Okay. I just want to reconfirm that everyone can see my slide. Someone say yes.
Yep. Yeah.
Yeah.
Okay, good. Kind of hard for me to like wait. I got 10 or 15 minutes into a class one time and everyone's like, hey, you know, you're lecturing to a blank screen. Oh, thanks. So accuracy check, I will fully admit, based on Sean's dad and several other airline pilots that I've talked to, that this particular procedure, doing it in real life, is a bit antiquated, but understanding it is not. So an accuracy check compares your short-range navigation like VOR, ground-based, to long-range navigation systems that you're going to use to get across the Atlantic Ocean or the Pacific, as the case may be. So what we're going to do is we're going to compare our flight management systems and GPS systems and INS systems. That solution, we're going to compare it with a radial and DME off a chart. And this maneuver, this accuracy check procedure, is a pre-flight tabletop exercise. So you will do this with a check evaluator. You might do this with your interviewer. In fact, if anyone knows Roy Evans, do you guys know him at all? Anyone on the, I think it's the Envoy Cadet program that he runs? He told me during his major airline, his Delta Airlines interview, he actually sat down with the table across from his instructor and had to explain how to do an accuracy check. So this concept still does exist. You know, as we phase out VORs and everything is space-based someday, it might not, but I feel like it's still a valid concept to teach. So what we're going to do is we're going to take our NAP-MAP chart out, handy NAP-MAP chart, which is pre-drawn with your course. Your route of flight from your Philadelphia to London Heathrow project should already be on there. Now for your project, it's helpful to highlight your route. So I'm not saying you have to highlight the route. I've suggested that you highlight the route. Make sure you've actually got everything on there perfectly. Double check that you're not using the H or the half distance waypoints, please, before you highlight your route. It should be all the waypoints all the way across from Connie to Coke on your flight plan. So if you're at home and you're listening to this lecture and you go, oh my God, I haven't plotted yet, hit the pause button, go to your computer flight plan and plot the entire route of chart, plot plot the route of flight from Connie to Point Coke. All right, now that you're back with me after pausing, we're going to account for slant range error. As we fly from Connie to Supri, take a look at your charts. It's very, very helpful during this lecture to have your charts out because I'm practically going to feed you every single answer on your project. Okay? All right, so from Connie to Supri, you are going to be flying just beneath the last little bit of land. So you're going to be flying beneath Nova Scotia, to the south of Nova Scotia. You're going to be going, say, just within range of Yarmouth VOR. You're going to be within range of Halifax VOR. Sydney VOR is just a teensy bit too far, but it might be within range if you measure it right. Which you're going to use your handy, this is my scrap paper, and you're going to lay it down and just check real quick, you know, somebody tell me what's the high altitude VOR service volume? What is it? Anyone not on mute? Anyone? Come on. Thomas knows. Hi, Thomas, you're here.
From 1,000 feet to 14,500, it's 40 nautical miles. From 14,500 to 18,000, it's 100 nautical miles. From 18,000 up to flight level 450, it's 130 nautical miles. And then from flight level 450 to flight level 600, it is back to 100.
Perfect. So what you said, what I heard you say is 130 nautical miles is pretty much your maximum range from a VOR while you're flying this route, because we're going to be flying at about 360, flight level 360, right around. So from Sydney VOR to our course line, which I have drawn, I have a little tick mark now on my piece of paper. I'm sliding that to the nearest measured tick marks, and I'm seeing that it's 100, let's see, almost 120, 110 nautical miles. So technically on your final exam, the Sydney VORTAC would be fair game if I wanted to give you an accuracy check to do on the fly, on your own. So, and I will warn you right now, it's very imperative that you understand this process of doing the accuracy check. I want to get you guys to the point where you understand it well enough that you can do one on your final without having done it before. But to be smart students who want to go into a final exam fully prepared to answer all potential questions, I would tell you that between Connie and Supri, there are only so many VORs within range. Hint, hint. Okay. I will tell you right now that I don't think Torbay is within range. If you take a look at the chart here, yep, that's well outside of the range. So the only three that I could potentially throw at you would be Yarmouth, which is the one you're going to do for your project, Halifax, and Sydney. Okay. So basically, as we fly this leg, we are going to take our last chance to compare a VOR radial DME that we have pre-flight planned to center up on our CDI. And we're going to compare that solution to the solution on our flight management. On the slide, you can see the rule of thumb is that if you're at 37,000 feet, you want a VOR at least 37 miles from you because you don't want to be in the cone of confusion. And obviously the cone of confusion gets bigger as you get higher in altitude. All right, so for this slideshow, what I have is an old version of a project, so I didn't want to give you any of the answers that you're going to have to find for your own project. This is a totally different project in which we are actually still flying Philadelphia to Heathrow. This is my old one. But instead of flying south of Nova Scotia, we're actually flying north of Nova Scotia. So all the VORTACs are actually beneath us. They're to the south of us. So it gives you an opportunity to see how to do an accuracy check on your project with VORs north of you and on this slideshow with VORs south of you. First step, and I know I told you that you're going to do practically everything on the North Atlantic plotting chart, but in this case, you're also going to use the Atlantic orientation chart for no other reason other than to look up in the list of VORs what the variation is. So on this day, when I made these slides a couple of years back, the Sydney VORTAC was at West 22. Can someone actually pull out their AT or their Atlantic orientation chart and tell me what today Sydney VORTAC is at? Jake, do you have your chart out? Did you say you have your AT orientation chart?
I do.
You do, okay. Do me a favor, just so that I can get y'all involved in working here.
So it's West 19.
There you go, beautiful. So my slide is actually, it was correct I think it was 4 years ago when I made this. But it's changed, now it's West 19. So I've redone all the slides since then, and we've looked at West 19 instead. So the old project that I used to run, we actually hit Point Tusky and went to Point Dottie, and this is the leg on which we did our accuracy check. Now, if you look at your plotting chart today, Dottie's gone. They actually removed a whole bunch of points and changed them to other things. So, you know, it's a matter in my job of keeping up with the latest changes. But so we're going to plot a north-south true line on the plotting chart. From Sydney. See where Sydney is here on the slide? To our course line. That's what we care about. And I know the green line's a little bit, it's imperfect because my PowerPoint skills are not great, but the bottom line is we're going to take our little scrap paper, and you guys can follow along with me. It's good. You can go back and watch this while you're doing it too, if you're not doing it right now with me. From Sydney to the course line in this example, you're going to measure that with your scrap paper, and we're going to find, hey, look at that. It's almost exactly 130 nautical miles. Notice, once again, I'm going to go back. You can see with my imperfect PowerPoint skills that I've got 1, 2 boxes, and then just a little bit extra. So I've rounded to 130 nautical miles, which translates into 2 degrees and 10 minutes. Everyone still tracking on how to do this?
No.
Remember how to do lat long math? Did I hear Kathy say no? We're going to do a little bit of math with lat longs. So what we're going to, well, who is that? Did someone
Sorry,
say?
I came in late, so I got kind of lost.
That's okay. That's why we're recording it. And I will stay after this class or in between classes, whatever you need. I'm going to be here at noon every single day live for you to answer any questions. Like, here's the deal. Like, this is real, right? You're going to have to actually do this. And so I know for a fact that during the concept lecture, a lot of this will just go right over your head. And then you're going to be doing it on your own, and you're going to go, oh, okay. Or you're going to go, I have no idea what she's talking about. I need help. And then you're going to come see me. Or you're going to see Michaela, who's a great resource. So back to the concept of this. We're going to add or subtract. No worries. Don't worry. From the lat long. How do we know that Sydney VORTAC is at 46 degrees, 9 minutes, 0.2 seconds? Does anyone know? Remember this? Matthew, you're not on mute. Tell me, how do I know this?
Well, wouldn't wouldn't that information be on the orientation chart?
It sure is. It's right there, actually. I'm trying to get my phone to focus so that I can take a quick shot of this. All right. So here we have, I'm going to blow it up and I'm going to put it in the screen. Oh, my phone's rotating. Dang it. It doesn't, it's not cooperating, but you see the lat longs right there beneath the VORTAC. So it's in the box. That's where I pulled this from. And so we're adding 2 degrees and 10 minutes. And let me go back to the slide where we show my route of flight. Why are we adding? This red line's my route of flight. There's Sydney. Sean, Logan, anyone?
Why are we adding?
Why are we adding instead of subtracting?
Because it's west variation instead of east variation. You add west, or is that a question on the variation or the?
No, we're actually adding 130 nautical miles in terms of its degrees and minutes. We're adding it to get our position. We care about where we're going to be, right? Okay, because Sydney's south of us. As you travel upward on this chart, you're going to add lat longs. That makes sense?
Yeah, that makes sense. I thought I was confused on what we were adding to it.
Oh, yeah. So actually, you're right. I'm going to get to variation in just a second. Right now, we're focused on a north-south true line on a chart. True is not mag. You can't read true on a compass. So yes, Sydney vortex at west 19. So we're going to have to add west 19 to what our radial DME will be. And that brings me to a point. Actually, tell me, Sean, if I'm here and my CDI is centered on Sydney, what's my radial DME at that moment? We sort of did this in class once. I introduced it generally. Tom?
Would it be 0, 2, 1? I always get which way.
So west 19 is our variation, and regardless of whether the airplane is north or south of that vortex, you're still going to add it. So what would be my radial here if we're due north of it? So we're on the tail of this thing. Think about where my arrow's pointed at it, right? I'm on the tail of it. What's the tail going to read? This is old-fashioned VOR skills, right? Someone help me.
019.
Correct. So our tail is going to be on 019. So our course that we set into our course window is 019. I'm letting it sink in. Does that make sense? And our DME is
130.
yes. We need to be at the 019 at 130 DME. Now, in turn, imagine just for a second, like you will in your project, because we're flying south of Nova Scotia. All of the VORs are north of us. So if the VOR were situated where my mouse is spinning right here, okay? If it were north of us, then what's my radial?
Is it still 019? Because you told us that we have to add no matter if we're north or south of it.
No, we add to the radial, but what radial am I on? If my airplane is sitting right here, I wish I could draw on this slide.
Oh, right.
We're on the 019 radial down here. We're on the what radial up here? If it's a true radial of 180, so it's due, we're due south of it true, we're going to add the 19 west to the 180. We're going to get 19. What?
199.
There you go. 199. I paused there because I literally couldn't do that. So if we're exactly opposite, say Sydney just moved 130 miles north of us instead of 130 miles south of us, we are going to be on the 199 radial. I'll pull up my whiteboard in a second and I'll show you. Okay. So instead of being 2 degrees, 10 minutes adding like this one, we would have to subtract 2 degrees in 10 minutes. The whole point here of this exercise is to get our lat long. So at the point at which we arrive at a north true, exactly on the true line above this VOR, the Sydney vortex, we're going to be at 48 degrees, 19 minutes, 0.2. West 60, 03.3. And why did the west remain the same, Mo? Thanks for joining us. Is Michaela behind you whispering the answers?
No, she's not here, but can you repeat the question?
Tell me why, in this case, and in every case when we're doing an accuracy check, why is the west not changing? Why is that remaining the same? I know.
Because of it's a longitude coordinate, so it doesn't change.
It's because the way we do an accuracy check, we're putting ourselves directly north or directly south of that VOR on purpose. So we don't have to do too much math. We don't have to do any west or east navigation here. We're arriving at this point over Sydney, hacking our FMS. Your flight management system readout has a hold button. So when you go into the flight management system, you're going to hit that hold button at the very second your CDI centers. And then you're going to go and you can compare all of those lat longs to what you found right here. Okay. Everyone understand that? This is where we should be in the theoretical perfect world, where our VOR is aligning with our GPS and our INSs are perfect. Mostly we're checking our INSs, our inertial navigation systems, because those things drift. These days, GPS is pretty accurate. In my day, GPS could be a little inaccurate from here. You could be 300, 400 yards off in a car, and even further than that in an airplane, but these days it's pretty good. So, so conceptually speaking, hopefully we're tracking that. If we're on the 000 true line with 19 west variation, we're going to be on the 019. That's the example I'm showing you. When the aircraft crosses the radial, the CDI centers, note the DME, because if you think you're supposed to be at 130 nautical miles from it and you're at 115, you're 15 miles off, that's no bueno. Then you press hold on the FMS display, and voila, you've got 3 INSs in this case. INS 1, 2, and 3, 3 redundant systems. Can anyone point out what is wrong with this picture? Which one's off?
INS2.
Yes, it is. It's got an asterisk by it. And even in the old antiquated systems, the asterisk means the computer has recognized that it's drifted and it's taking that out of the equation. So it's not allowing the INS2 to pull the solution off. Usually what happens in an airplane is your INS solution and your GPS solution for where the airplane thinks you are. They will basically provide an average. So the airplane works off of the average of all of them, which, if you think about it, it's going to be the most accurate. If one of them starts to drift, and INSs do happen to drift quite a bit, the new laser ring gyro IRSs are much better, but you may be flying something in Allegiant Airline. Who knows what you're going to be flying over the ocean? You never know. In this case, we're way off. It's taking it out of the solution. You still need to understand, based on some of the previous lectures on international navigation, how many long-range navigation systems do we need to be able to go out and fly over the Atlantic Ocean on a North Atlantic track? Does anyone remember? Minimum? Not that you'd ever fly with the minimum? No? Okay. I'll remind you that you need 2 LRNs, 2 long-range navigation systems. So you're going to have at least an INS and a properly working GPS. Most airplanes will have many more than that, at least several layers of redundancy. Because if this INS2 is off by 2 degrees, imagine this was factoring into your solution. If your flying time to get to that point was 2 hours, so we've already gone 2 hours and it's off by almost 2 degrees. How much further could INS2 drift in 8 hours if it was drifting at the same rate? Anyone good at math? I'm calling you again, Tom, because you're good at math. How far could you be off, mileage-wise? Think about it. How many nautical miles? It should be pretty simple math. 2 degrees in 2 hours. Just multiply that 2 degrees times 8 instead. So 60. Anyone not get 480? 480 nautical miles off your planned course. So a degree is basically 60 nautical miles. So if you're off by 2 in 2 hours, you could be off by 480 in 8 hours. That means you miss lodges completely and keep trucking on into the middle of the Atlantic Ocean and end up ditching your airplane, at worst. And we all think like the worst case scenario could happen when we're flying an airplane. If you are not the slightest bit nervous when you launch out over an ocean with nobody watching you on radar telling you where you're at, you should probably check your head, because it is a very nerve-wracking experience. No matter how awesome and modern your systems, it's important to check them. So this is what we're doing. We're checking our solution, and see where the little black dots are? Those are our plots. Back in the old days, not to call out Ron Carr or anything, but back in his day of flying in the airlines, you no kidding plotted your INSs. You know, while you're flying into the middle of the Atlantic, while you're leaving, you're plotting where your INSs are. In this case, we got one way off. Okay, so we wouldn't go. I wouldn't go. Okay. Here is how you can plot this in real life when you're sitting there in an airplane plotting the accuracy check. What do I want on your project, you ask? Of course you ask me these wonderful questions, right? I'm gonna stop my share for a second. I'm gonna show you a whiteboard, which is so much fun. See if I can do it. Do you see my whiteboard? Anyone?
It's, well, I just see you. Oh no, there it goes.
Oh, there it is.
Okay. We were doing a little bit of fun on the whiteboard. I suck at drawing on this thing, so like, welcome to 3rd grade writing here. Bye-bye, I'm erasing. So here's Philadelphia, here's London Heathrow. I'm not sure what all the scribbles were, but bye-bye, bye-bye. If you need some tips on how to plot the ETPs, I'm happy to go over it with you after class. So we got distance, I'm deleting. Okay. On your route of flight, on your project, these are VORs. Do you like my VORs? Pretty, right? Such a great artist. See these things? Okay. Imagine we have one down here too. That's Halifax. Oh my gosh. All right, never mind. That is ugly. All right, my point in pulling up this beautiful whiteboard is to show you how I want you to plot this. Okay, mind you, you are gonna use an actual straight edge. I repeat, you will use an actual straight edge on my route of flight here. Let's pretend this is a solid line. Oops. Okay. We're gonna plot, how do I rotate these? Shoot, never mind. I'll have to plot it like this. Pretend we're doing our accuracy check off this guy right here. So we're gonna, draw our north-south line perfectly to our course line. And on our course line, we're gonna draw a triangle. Triangles are how we annotate an event on our flight plan. Okay, did that work? Okay, just pretend it's a perfect triangle, all right? Then we're gonna, whoops. I would not be a good YouTube star. All right, so we're gonna take it down because the flag needs to go down because the top is a little too cluttered. And I'm gonna make several prongs to my flag. Okay, now on the bottom one, the top one here, oh boy. It's supposed to say accuracy. You like it? Is that beautiful or what? Okay. Then, and this is the required elements on your project. So pay close attention. Here you're gonna get me a Zulu time. I'm putting X's here because you're gonna have to figure it out. I want a 4-digit, whoops, God, Zulu time. You need your time of arrival at the accuracy check. Got it? All right, next, you're gonna take and let's say this is Yarmouth. Let's pretend. That is Y, Q, curved lines are very difficult. I, YQI, and then you're gonna write your radial, whatever that is. And you're gonna slash, and you're gonna write DME, whatever that is. Okay. The radial, where, someone tell me, where did I get the radial of YQI? We can do it together real quick if you want answers on your project. Tell me the variation at YQI, which is Yarmouth. Oh wait, this reminds me of a real class actually. Like, somebody tell me the answer.
West 17.
Thank you, Matthew. Thank you so much. So we are gonna write, whoa, that's huge, but that's all right. West 17. So tell me, Matthew, while you're off your mute here, what should my radial DME be? We don't know the DME yet. We need to measure it, right? Off Yarmouth.
Yeah.
I'm south of it. This is the brain twister.
197.
There you go. I was going to say, anyone can help him. So I'm going to take this and I'm going to go click, 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 erase, and I'm going to make it 197. Now your task, should you choose to accept it for your project, is to get a DME for me. So from Connie to Supri on that leg, if you've measured it out properly, you should get a DME of approximately. Anyone want to give the answer? Someone help me out, measure it out. Otherwise, I'll keep moving and you guys can just do it on your own later. Tell me to stand by. I'll move on. I'll give you a clue. It's a really easy DME to do lat long math with. Hint, hint. All right, I'm gonna stop the share on the whiteboard. I'll move on. That's okay. I don't expect anyone to be super fast with calculating that. We'll get there. I'll show you offline if you want to stay for a quick bit of office hours afterwards. Got it measured out on your chart. Are you guys seeing the slides one more time? You guys seeing this?
Yeah.
Okay, so we figured out, I'm gonna kind of go past this a little bit because we're actually working on our own project there. We figured out that we should be on the 197 radial off of Yarmouth VOR. What we didn't do, and I could do all these examples, but I think it's almost more important to do examples off of our own projects. So keep going, keep going. So distance, this is an example of the opposite where we're actually subtracting 2 degrees in 15 minutes. In case you guys have forgotten how to do lat long math, this is something that it hurt me the first semester I tried to do this because it's not your typical borrowing situation. You're gonna actually have to say you're taking 15 from 13. You have to borrow a degree from the 50 and add what to the 13? Anyone?
60.
So you end up with 73 minus 15 is 58, and then 49 minus 2 is 47. Okay. Don't hesitate to get help. Okay. So for accuracy check, oh, okay, this is my old project. I'm gonna keep going. We'll actually figure that out together in just a sec. Oops. Last chance. So gross error checks. I'm going to gloss over gross error checks here. If you have a burning desire to know what a gross error check is and really understand it to your fullest extent, I'm happy to show you. What it is just in quick 10-minute synopsis of it. What I do in class is I just say, look, if you ever ask what a gross error check is, by an old guy probably, you're going to just say that at that moment in time, when you want to do one, you're flying already. It's not a pre-flight tabletop exercise. It's real life. You don't know where you are, which is like highly unlikely these days. Imagine you're picking up the YJT VOR and you're like, I don't think I'm on course, so let's check to see if I'm on course. And you center up your CDI right then and there, and you're on the 051 radial at 53 nautical miles. So you plot yourself on the chart using the 051 radial that you just figured out because you centered your CDI, okay, and you subtract the variation because you're west, and west is actually subtracted from mag to get true. So you got a 030 true line to plot. You pull out your, does this sound a little far-fetched that we're going to pull out our handy trusty plotter and we're going to put a 030 true line, strike it right through our course line? Anyone like, oh my gosh, right now? And then you measure 53 nautical miles and you go, bam. And on the chart, from your known position at 051 and 53 nautical miles, you would plot it and go, okay, did that line fall on my pre-flight planned course line? And if the answer is yes, then you are on course. If the answer is no, then you've got some sort of error. Questions on gross error checks? I know what you're all wondering. Is she going to ask me about that on the final? Does anyone know the answer? Sean, tell me. Am I going to ask you about that on the final? No?
Probably yes.
No, not at all. I'm going to go back and I'm just going to reinforce the fact that gross error checks are indeed rather antiquated. And I've never, and in fact, I asked Roy specifically, have you heard of a gross error check? And he said, yes, I have. And I said, have you ever been asked about it in the airlines? He says, no, I haven't. So at that point in my career as a professor, I said, you know what? I still want them to know vaguely what it is in case someone does ask them, but I am not going to quiz them on it. So no gross error checks on the project. You'll notice in your project 2 answer packet, there's not a single thing in there about gross error checks. I am not going to spring it on you. I will spring an accuracy check on you. You will have to do one off of one of those 3 VORs that I pointed out. Okay, so moving on, there's something else we need to plot as you're flying over each waypoint. And this is kind of old school. Once again, we used to have paper computer flight plans and now we have ForeFlight. And of course, it's still sort of a similar concept that we care if, you know, if we're in this spot right here, we're going on to the next waypoint. If our FMS doesn't trip properly, we're gonna have to do some troubleshooting, right? We gotta figure out where we're at. So just after waypoint passage, this is a tried and true old school sort of checklist. Even when I was flying across the Atlantic, you cross every T and dot every I and make sure that you're always on track, because you can't just zone out and watch a movie while you're flying an airplane in non-radar controlled over the ocean when your navigation solution is so very important for your survival. So just after each waypoint that you reach, you check your position. This is something Sean's dad could probably tell you that they still do. They still check their position, even if it's all internal to the aircraft and it's all like PBN and there's a system checking on itself, make sure the cross-track error is not too big. Pilots still do a changeover briefing. So imagine I'm the captain and I've been flying for 6 hours or whatever, 4 hours, and there's a captain in the back deadheading and he or she's asleep, right? And they're coming up to take over for me. I'm going to do an actual position check before I hand her the controls. I'm going to say, all right, I have already, I've checked that the FMS trip to the next waypoint. This is where we're at on the chart. Autopilot is still coupled. That's confirmed. Treat autopilot as if it's a human and treat it as if it's a toddler. Does anyone have a toddler at home? Anyone ever babysat before? Nobody?
Oh, yeah.
Yes.
Okay, so most babysat. So if I gave you my 2-year-old to watch, would you just let her run around the house?
Nope.
What if there was,
No.
I mean, what if there were knives, right? Your autopilot, I don't care how advanced the Airbus is that you are flying, your autopilot should be monitored as if it is a child flying the airplane. You always make sure it's coupled in the proper mode before you hand it off to someone else. Did you know this? If you get up to go tinkle in the back, say my autopilot's connected on my side, you know I have to transfer the autopilot to my co-pilot, right? I can't just let the autopilot fly and get up and go pee and come back. So I know this is totally digression, but it's important to understand that autopilot is treated as if it's an extension of you, the human. So if your autopilot's coupled on the left side to all your PFD instruments, you say, all right, transferring aircraft control, you also transfer autopilot control. So then you compare what you're flying to your planned headings. This is kind of important because you can catch wind, unplanned wind doing this. I caught an unplanned headwind of about 110 knots once that actually forced us to divert to Kesselvik by doing a waypoint passage check. So we hadn't noticed anything really all that crazy until we got to the waypoint and we're like, holy crap, we're way behind. We're like several minutes behind. What is going on? So we sat down and just made a decision to divert. Record your significant met data, your whatever's going on weather-wise in Heathrow. You're going to need to know well in advance, because if there's a reason to divert for weather, you'd much rather know when you've got enough fuel to divert. Does that make sense? Okay. I'm not being sarcastic, really. The sooner you know the weather's going to be a problem, the better it's going to be for you. So it goes so much smoother, and you'll find this out someday. It goes so much smoother if you're ahead of the airplane, and it's a very challenging thing to do in this dynamic situation. So you also compare altimeters. You know, if the other pilot is completely asleep and they don't notice that their altimeter is 200 feet off of you, this could be an issue. So always check. Make a position report. Nobody knows where you are unless you tell them. And then X through the old waypoint and keep going. All right, hit that one hard enough. You also write down your fuel consumption. So it's basically, you call it scoring or whatever. I'm sure these days it's on an iPad, but you have to type it in. Sometimes I've heard that you actually have to tell dispatch each time you reach a waypoint how much fuel you have. They're monitoring you too, and they're writing down your progress. There's you compare your pre-flight to your actual fuel burn constantly when you're flying over the ocean. It's really important to understand you may have a fuel leak or an unplanned headwind, and there's a really small margin of error before you're going to be diverting. I can tell you that from personal experience. I was trying to get to Goose Bay, which is in Newfoundland, and there was no way I was going to have enough fuel with an extra 110 knots of headwind. So after waypoint passage, you just make your X, and then you keep proceeding. Now, the 10-minute check is something that not every airline does. Sean's dad can probably tell us. Sometimes it's a 10-minute check. Sometimes it's a midpoint check. But in between each two waypoints, you're still going to do a check to make sure you are where you think you are. The airplane may also tell you with alerts. But back in the day, we'd plot the FMS, our blended position, on the plotting chart, like for real. We'd look at where our FMS said we were at, and we literally sit and plot it. It makes sense when you don't trust the GPS 100% with your life. So if it's on the line, you're good to go, keep flying. If not, what I would do to troubleshoot a situation where I'm not on the course line I planned is I would take a look at my solution and see if there's something that I can eliminate that's pulling the solution off. So if one of my INSs has drifted, which has happened to me on numerous occasions in a C-130, I say, hey, nav, I'm going to hold wings level, and I want you to align INS number 2. So it takes a little bit of crew coordination. Sometimes it takes ATC coordination. If you happen to be on a leg that's a straight and level leg, you can just do it. But I've had many INSs drift. So you don't want them to pull your solution off. You don't want to be off course over the ocean. I know that's pretty self-explanatory, but when you're trying to visually pick out, and of course there's GPS backing you up, but visually picking out an island system, it's not as easy as it looks. Here's how you annotate a 10-minute check. You will have to do this on your project. You make a flag, you make a triangle. This triangle waypoint is called an event. So we're having an event at a 10-minute check. Now, I could be mean and rude, and no, just kidding. I could be more thorough with you, and I could force you to do a 10-minute check and plot it after each and every waypoint that you pass over the Atlantic Ocean. I mean, it has occurred to me that that is more realistic than what I have you do. And actually, my lack of realism, my dumbing it down for you actually causes some people confusion. So we're just doing one 10-minute check just to prove that you can plot it properly. And it's easy because, say this is one of our waypoints, 53 north, 50 west. On our computer flight plan, it's going to tell you what time you arrive at that waypoint, right? So it says what time in terms of time elapsed. So if you arrive at this waypoint 3 hours into the flight, you're going to arrive at your 10-minute check at 3 hours and 10 minutes into the flight, right? So the only like semi-complicated step after that, knowing that you arrive at 3 hours and 10 minutes into the flight at your 10-minute check, is giving me a Zulu time. So does anyone know offhand what time we take off out of Philadelphia in Project 2? I know, oh, did he leave? Jake, we just looked at it. Do you remember?
I am here. But no, I don't remember.
I have it memorized, which is kind of sad, but I'll show you. It is 0025. So we actually, and while we're at it, I'm going to point out to everyone else. Oops, page 7. Where's page 7? Shoot. Oh, that's the ETP homework. That explains why. I can't find it. Toby, seriously, do you guys hear my dog behind me?
Yeah, a little bit.
I wasn't sure if that was your dog. It's got an interesting bark.
Boring. I'm putting him to sleep. Mute your mic, man. That is just rude. Just kidding. Okay, where's my page 7 of 10? 0025. Okay. Why is it still, I'm still on the homework. This is why I'm like, you guys, I'm really retarded when it comes to this stuff. American Airlines, dispatch release. 0025. Please give me what I need here. SKD, look at that. There's another way to find it. Here on page 7 of 22. Y'all following with me? This is the most important page of this whole project. Well, arguable, but this SKD here, this scheduled time of 0025, that is our actual takeoff time. It's also what they put on the Expedia or the Orbitz to tell passengers what time they're going to take off and generally what time they can expect to land. But this scheduled time, I don't know why American Airlines decides to put it on here at all for land time. 0745 has nothing to do, no bearing on reality. Jake, explain to everyone what we talked about. What does have a bearing on reality? What time are you actually going to land?
Well, it's not that number. That's the ideal time you want to land, but you want to take into effect the wind and all that junk. So it's going to be later than what it says.
How much flying time are we going to do based on what I'm showing you up here?
The 7 hours 2 minutes.
Yes, indeed. 7 hours and 2 minutes is how much flying time we're going to do. So somebody tell me what our planned land time is actually going to be. Zulu. Lee, you're not muted. Tell me. 7 hours and 2 minutes after we take off at 0025, which is a Zulu time. So 25 minutes after Zulu midnight, we take off and we fly 7 hours and 2 minutes. What time do we land? Tom?
0727.
Yeah, indeed. 0727. That's an answer on your project. So I ask you, what's your planned land time? It is actually 0727. So why is 0745 even printed on the schedule? Don't ask me. Even Peach Lichting, who gave me this dispatch release, has no idea why they bother printing it. I'll point out a couple other things while I have you guys here. Ground time of 23, that's at Philadelphia, and 9 is at Heathrow. This is your cost index. So these things I pointed out when I went over the project, but they do crop up when we're doing accuracy checks. Excuse me, we're doing accuracy checks. The one reason you're going to need to pull this up and look at the computer flight plan is because I'm going to ask you to give me what Zulu time you arrive at that point of the accuracy check. So if we're doing the one off Yarmouth, we're going to have to plot it based on how many miles it is from Connie. and we're gonna have to do a ground speed problem. Eek! Eek! So where's Connie? Let's just do this together, okay? I'm gonna shortcut you through this project. I'm gonna help you out big time right now. We're gonna go to Point Connie. Connie's here, and Supri's the next leg. So somebody tell me, based on looking up here at this ground speed, and disregard this. I'm gonna delete this right here. This is something else we were talking about. Okay, which ground speed are we going? Are we going 484 or are we going 550 on that leg?
550.
50.
Thank you, perfect. So we're going 550 between Connie and Supri. And when you get to the point where you have plotted your point of the accuracy check, you're gonna take out your handy paper and you're gonna say, oh, look at that. It looks like it's about, it's about 50 miles. Shh, did you hear me? It's about 50 miles from Connie. 50 miles. Okay. Wake up. I'm gonna go to my whiteboard. I'm gonna show you how you do this. Just in case y'all have forgotten how to do a time, speed, and distance problem. Can you see the whiteboard? Confirm?
Uh-huh.
Okay, cool, thank you. So right now we're gonna sort of do this together. So let's pretend Connie is here. That's my Connie waypoint. Okay, I'm gonna draw and I'm gonna point an arrow at it and I'm gonna say that is Connie. Okay, so from here to here, I said it was a D distance that I plotted of what? 50-ish. You can get slightly off this, that's fine. Now what's my V? What's my velocity?
550.
Thank you, 550. So give me my T. How long does it take me to get from Point Connie to our point of the accuracy check? Anyone have a trusty calculator? Or I know that you're scared of this, but hey, there it is. I'm showing you in my cam what you can use to very quickly find this out. What's my rate that I'm supposed to put under this black arrow? Anyone? Tom?
550.
Yeah, my rate of speed is 550, and I just went ahead and put 55 underneath the 60 rate knob. And I'm going to attempt to find the time based on the distance that I plotted. 50 is across from, let's see, 4, 5, 6. It's about the inner ring. Your inner ring is your time, and your outer ring is your distance. Just to remind you, we have about 5:45. Do y'all agree?
Yeah, I got about 5.5
Yeah. So I'll
in
go
that
to,
range.
we'll compromise. We'll go with 540. That's fine. We're gonna round anyway. I'll tell you the truth. It's not worth your effort to nats us this too much. We're gonna round up to, since we're in between 5 and 6 minutes, you can use either one. Let's just go with 5 minutes. Cool, easy peasy. Why do we care about this 5 minutes? Why is this so important? Right here is why we care. This is why. We want a Zulu time of arrival. So in project 2, I ask you to write down and plot what your Zulu time is at the arrival point at the accuracy check. But in project 2, does anyone know the curveball that I throw you? Anyone been dug in that deep yet? Tom, have you looked at this problem yet? The accuracy check problem?
Nope.
Okay, I'll show you right now. So the question I'm gonna ask you is, at what time do you arrive at the accuracy check if you take off 10 minutes late? Our takeoff schedule time was 0025. Okay. So if I arrive at Point Connie per the, I'm gonna stop sharing and go back to sharing my other screen here so I can show you how to do this. If I arrive at Point Connie And my time elapsed here, sigma time, sigma distance, let's see. We are an hour and 3 minutes into the flight, right? At Point Connie? Everyone agree with that? Okay. Hour and 3 minutes into the flight, regardless of when we took off. So if we took off at 00:25 or 10 minutes late, 00:35, it still takes us an hour and 3 minutes to get there. But what changes is our Zulu time of arrival at Connie. So what is our Z time of arrival, Tom, at Connie? I'm picking on you today because I see you're not muted. I mean, 25 minutes plus 3, right?
You said 10 minutes after?
So but first, I'm just asking the basic question. What's our Z time or Zulu time of arrival at Point Connie?
Uh, 0128.
Yes, 01:28. Add 5 minutes.
Okay, 0132
Zero
or
one
33.
three. There you go. 0133. Is everyone tracking on why we have 0133 and why this is an important number for us? Rita, my dear Rita, I'm gonna pick on you just because you guys came to live class. Several people asked me to do live class, so I'm picking on you.
I kind of was lost there. Sorry.
Okay, that's all right. It's okay to be lost. Just let's find you here. We want to know what time we arrive at Point Accuracy Check, which is a big event for us. We're going to do this huge accuracy check. It's going to matter.
Was it because of the time delay? That's why.
Well, this we had to do several levels of calculation to get to this point. First, we figured out what Z time we arrive at Connie based on this computer flight plan that we have, and we got 0. Based on our original takeoff time, it would have been, what, 0? Gosh, I've already forgotten. 1:28.
128.
Yeah. And then we add 10 minutes because we're late, right?
Oh, that's right. Okay.
Then we add 5 minutes because from Connie to this point is 5 minutes. Did we add the 10 minutes, Tom? We didn't, did we?
No.
No,
See?
yeah.
You guys caught me in the middle of a screw up because I asked you to do Connie, the Point Connie, as if we took off 10 minutes late. If we took off on time, your first answer would have been right, but we took off late. So it's 0. Oh my gosh.
So it'd be 0143.
Correct. 43. You see my beautiful writing, Rita? All right, so we've gotten this.
Thank you.
That's 50 miles. I meant that on my nap chart. Okay, and it's just too stupid to even leave on there. I'm gonna take that off. Okay, that's 50 nautical miles from here to here. Okay, and we figured out with the time, speed, and distance calculation, which you're gonna have to do on about, I'd say 5 different occasions in this project. You're gonna have to do this very simple time, speed, and distance problem, pulling ground speed off of your computer flight plan. Okay, so the other, back to the original slideshow that we were talking about. Let's go back to the accuracy check slideshow. The other things we're gonna wanna annotate on our accuracy check flag. I think I'm gonna have to stop the share real quick. Go back to screen 2. So accuracy check flag. Obviously, you can't plot your INSs because you don't have a real airplane. Makes sense? You can plot the VOR lat longs, and you can plot YQY or whatever your radial DME is for your Yarmouth VOR. You plot your Z time as per the project. When I ask you to answer that you're late, you're going to put that on the 0143. And then you're going to put accuracy check on it. Questions on what I want on Z project? Okay, feel free to ask me later if you're too shy in class, that's fine. All right, so a 10-minute check is going to be at least 1/10 the amount of effort as the accuracy check was. The only kind of complicated part of this, and I get a lot of questions on this later on, the only semi-complex thing you're going to have to do here is find the latitude and longitude of the point. I'll tell you right now, there's no easy way. You just have to look at where it is, where you've plotted it, do a time, speed, and distance calculation from the previous point, 10 minutes, however fast you're moving, and plot it, and then eyeball it. And give me as accurate as you can. Questions on how to do that? Anyone? You guys are like crystal clear here with what you want, what I want. I'm gonna ask you to do an accuracy check. So for the project, and then I'm gonna ask you to do one during the final. And then I'm also gonna ask you to do a 10-minute check prior. So on your answer sheet, there's a 10-minute check. And then I'm gonna pick a different waypoint. And I'm gonna ask you to do a 10-minute check during the final. Okay? Okay. I just gave you all the surprise questions you're gonna get. You're gonna get one accuracy check to do that you didn't do prior. You're gonna get one 10-minute. You care if you're one of those people that's like, man, I need an A+++ on this final, I would just go ahead and do a 10-minute check with a flag after every single waypoint. Another option for checking your position in the airlines is a midway or a midpoint check. Done similarly to the 10-minute check, you just plot your FMS blended position and ask yourself, is it on the line? Do you need to revise your estimates? Am I consuming fuel the way I thought I was going to? And then once again, every waypoint, you get your coffee out, take your little snack, and you check weather in that order. Check weather. Weather checking, it becomes an obsessive thing when you're flying over the ocean, especially when you're flying to London. London, landing in London in the morning, as I'm sure Sean's dad would tell us, it can be very foggy, it can be very crappy, you can be down to minimums on the average day there. So pay very careful attention. I've flown into Shannon many times, and about 50% of the time, we were right at minimums for the ILS. So questions on accuracy checks or what I need from you for this project? Anyone? Silence. Just remind yourself there's a lot of people that aren't, that can't make it to live classes. So if you have a great question, now's the time. Okay. Alrighty.
Wait, sorry, I have a question.
Sure.
You know, for the project, how you sent out like the paper of the map. I don't have a printer, so can I just do it, I guess, on the regular map that we bought?
Are you talking about the ETP homework, Rita?
Yeah, sorry.
So the ETP homework, those maps, the charts are completely optional, like I said, in the ETP lab, because of the fact that not all of us have printers. So even I don't have a printer at home, so I'm not requiring you to do anything with the maps or the charts. What I want to see, if you do not have a printer, I'm going to show you real quick how you do this. Are you watching? Oh,
Yeah.
my screen shared? Okay. I always have to double check because, you know, you don't want to be that guy that's like talking to the empty screen. So notice I'm up here and I've got this, what do you call it? Pen thing. I don't want that one. I want, how did I do it before? Jake, how did I do it before? I had it figured out.
It was on the right side, maybe that little purple box.
This fill inside? Is that it? Okay, there's a pen somewhere. Where?
Hit tools, maybe.
Oh, okay. Back on the normal standard page that you open it up on, Rita, you're gonna see this little pen thing. That's a highlighter. See this pen? Looks like a regular fountain pen. Click on that. And voila, look, I've got text boxes everywhere I go. Cool, huh?
Yeah.
Text my name in and everything. So each waypoint, I know it's kind of labor intensive, but you scroll down and you say, all right, Morag. The next point is Mimku. I'm gonna type Mimku. And then I'm gonna tab over and I'm gonna go look at the distance between those two. I go Morag to Mimku is 19 miles. Cool. I actually gave you 171 to give you a clue on which leg to read. So 19 miles. So 171 plus 19, we're going to keep a running tab of how much distance we've traveled here. So it's important because you can't rely on the computer flight plan to give you the total distance on this ETP calculation. Does anyone understand why not? Anyone? No? Because the total distance down here, if you actually look at the TTLT, or where is it? LDR 1847, that's nothing even close to what the ETP is going to be, because we're not going all the way from Glasgow all the way to Shefferville. Our ETP is between Morag and Nain. Make sense? So we're like starting midway through. So fill in the data, right? Continue to fill in the data. Each point goes in there. Each segment distance goes here, and the total distance on this sheet goes here. You can disregard these lines. I was just giving somebody an example on how to draw a line. Okay. If you want to draw that line, like whichever two legs your midpoint lies between, hit this button and draw your line across. Okay, and then fill it all the way and make sure you show your work. You can show your work in the text box right here. Fun, huh? Once again, for everyone who may have missed my announcements or some of the videos where I keep saying this over and over, my due dates are very flexible. Got it? If you don't turn it in by tonight, not off with your head. Just work on it and get it right. Because tonight's the due date does not mean I won't accept it late for a 0 penalty, because we're all in a really rough situation here. And I know that this takes 10 times the amount of effort without a printer as it does when I hand you the piece of paper in class like I usually do. So, all right.
Thank you. Those columns that are like empty, do we have to fill in those?
Okay, the reason why those columns are empty, I'll show you right here actually on the lab. They're empty because they allow you an empty column to put your averages in. See this? So once you draw your midpoint line and you tally your ground speed for it and you tally your true airspeed for it, I'm gonna go back here and show you the PDF, and your wind component backwards, these empty categories over here, notice I'm gonna write average, and then I'm gonna do whatever that is. And then down here, whatever that is, see? So these are my spots where I have room to write my average numbers. Those average numbers are going to be really important, instrumental in the formula that you got to plug in, which if you guys just use the lab ETP here that I've posted on the modules under the lab, it says pre-coordinate if you're going to miss this class. Well, yeah, that's when we were all in person, of course, but notice my color coding it should really help you out. The color coding for average ground speed is right here. So average ground speed's plugged into the formula in the right spot. Average true airspeed's here. And then the wind component, notice it's a positive up here and it's a negative down here. You got to reverse it because of the concept that we're turning around at the ETP in theory and we're going back. Okay? Okay.
So I can have like one average number for all. Oh, sorry, whoever's talking.
Jake, did you have a question about that?
So, since for that equation on that right there, since it's all headwinds, should it actually be doing a plus? So like it's 536.4 because it's 495 minus negative 41. So it should actually end up being the 536 for the ground speed return?
No, that's actually a great question. That brings me to a really big confusing matter for some people that they don't grasp the concept of the formula. Just treat the formula as yes sir, yes ma'am, I'm just going to plug the numbers into the formula. What you've got here, see, it is a plus. That's correct. It is
but
a plus.
It's a headwind in our case, so it should be a negative.
No, it's not. Look at the ground speed here. We got 545 and 482. Our true airspeed is really slow and our ground speed is really fast. So we've got a positive here in these.
Okay.
So before the midpoint, we have a tailwind. And then In the formula, it has you reverse it because the ground speed to return is the value that we want there. This is ground speed that we're traveling on those two legs prior to return. Now, if we were at this yellow line on the flight plan, if we were to turn around and go back through that air mass, we would then have a headwind or a tailwind. What do you think?
Headwind.
Was that
Headwind.
headwind? So exactly. So we have to put it in the formula here, with the negative, as a headwind, even though it was a tailwind, those two legs, because the value is ground speed to return. Ground speed to turn around at that point and go back.
Oh, I forgot about that stage. Thank
Yeah.
you.
In a lot of ways, this formula is way over the average pilot's head, and we all admit that. We go, all right, I got it. I'm just going to go with Professor Height's color coding, because this slide wasn't even color coded before I got to it. I was like, I got to do something here because this is too complicated. So take these numbers, average them up. On your spreadsheet, you're going to have to find out. The first step is to total that distance. You know, from point Morag, or on your flight plan, it's actually 171.2 Morag, so that makes sense. So you're going to total your distances. Bam, right down here, write total distance. Whack it in half and draw a line. That's how you get your averages. Okay. I know this is a tough class to do even in person, when I can show you and I can point and I could say, you're doing this wrong. You forgot to reverse your winds. So hence my decision to stop and say, no, they don't need to do this on their final exam. We're just going to do a homework, which is, again, a flexible due date. Okay. All right. I need to stop the recording here and say, all right, this is the end of the accuracy check lecture. So we're going to stop the recording, and then I'm going to start the ET or the ETOPS lecture.